Welcome guys to the numerical point in which we deal with numericals to understand concepts, and the subject for today is fluid mechanics. Topic is capillarity, question number 2, and the level of the question will remain medium. And before we start, just hit the subscribe button, press the bell icon to never miss any update. So let's get started. Question reads like, what will be the value of capillary rise when an annular tube of inner radius 5 mm and outer radius 10 mm is immersed in a liquid of density 1000 kg per meter cube and surface tension is 0.020 Newton per meter and take the angle of contact as 45 degree. So guys, in the question it has mentioned the tube is okay, the tube is annular. So now let's derive the capillary rise equation for the annular tube. Okay, then we will put these values in that formula to get the capillary rise. Okay, now let's first derive the formula, then we will apply the formula to get the answer. So guys, this is an annular tube. Okay, annular tube means it has a uh, solid section in the middle and it will have a hollow section at the periphery. So this is hollow section and in the middle this is solid section. Okay, so this is solid and in the in the periphery there is a hollow section. Okay, so if you want to see the top view, then this is the top view. Okay, this is solid portion and this is solid portion and this is hollow portion. Okay, so now let's define the radius here. So let's suppose the inner radius is Ri and the outer radius is RO. Okay, the inner radius is Ri and the outer radius is RO. So in this, okay, in the front view, first let focus on the forces, and now let's derive the equation of the forces, and now let's consider the equilibrium. Okay, if you will see this portion of water, okay, this portion of water is under two forces. Okay, under the action of two forces. One is in the last class also we have decided, that is the weight of that water, and the second is the surface tension force. Okay, the surface tension force acts at the surface and the weight is acted at the centroid. Okay, so weight we simply know that is rho gv. Okay, rho into g into volume of this rise of water. Okay, so we can find out that easily, but now let's first discuss about the surface tension force. Okay, so guys, this is the close view of the annular tube. If you will see, this is the surface. Okay, this is the surface, and how the surface tension force will act. Okay, so the surface tension force will act tangentially. So at this wall, okay, at the inner wall, the surface tension force will act like this. Okay, okay, and the outer wall, the surface tension force will act like this. So here also the surface tension force will act like this, and in the outer wall the surface tension force will act like this. Okay, so now okay, and this angle, if we'll see, will be theta, and this angle will also be theta. Okay, so this surface tension force will have two components. Okay, one in horizontal direction and other is in vertical direction. So if we'll plot the horizontal direction, then this will be this and this will be this. Okay, for here this will be this and this will be this. Okay, now let's see the horizontal forces in the top view. Okay, so this is the top view. So the horizontal forces will act like something like this. Okay, Now I'm showing the horizontal forces. Okay, not horizontal, but the component of the surface tension force in the horizontal direction, something like this. Okay, something like this, in entire periphery of inner radius, and also in outer radius. Okay, one second. Here you can see the direction of the forces are inwards. So the direction of forces will also inwards here. Okay, I've shown it outwards, but actually it will be inwards. So now let's show the forces inwards. Okay, so it is equal in magnitude and distributed in entire periphery. So, and in the um, uh, outer side, outer wall, it will act outside. Okay, in this fashion. So one thing we can say, it is distributed in entire periphery. Okay, entire periphery, and equal in magnitude. Okay, equal in magnitude, so they cancel out each other. Okay, so they cancel out each other. So from here we can say the surface tension force, okay, surface tension force in horizontal direction will be 0. Okay, surface tension force in horizontal direction will be 0. So this is our one result. Now let's see what about the vertical direction. Okay, okay, in the vertical direction it will have components like this. Okay, so this is in vertical direction. So now let's see the vertical component in another view to get the complete understanding. Okay, let's suppose this is in another view. So from here the vertical forces will act like this. Okay, and all of them are in upward direction. So this is the vertical forces component of the surface tension force. Okay, are you getting it or not? So this is the vertical component. Okay, so the vertical component will remain there and they will not cancel out each other. And if we will see another thing here, so I'm showing the gravity also here. Okay, this is the weight. So this vertical forces in upward direction and this weight in downward direction will balance each other. So here we can write from our observation that the the surface tension force in vertical direction will be equal to weight. From here you can clearly understand it. Okay, so now let's find out the vertical component of the surface tension force. So guys, if this is the angle theta, that is angle of contact, then this angle will also be theta or not? This will be theta. So we can write the cos component of FST. Okay, this is surface tension force and this is surface tension force in vertical direction. So we can write from here, we can observe. Okay, I am writing here so that you can see simultaneously the FST in vertical direction will be FST into cos theta or not. Okay, FST cos theta is FST V. Okay, this will be used in our derivation. Okay. Okay, from here we have found out FST equal to FST cos theta. So now let's put that value here. So by putting that value here, FST cos theta will be equal to weight. Okay. Okay, what will be surface tension force? Surface tension force will be sigma. Okay, it will be sigma into the periphery on which it is acting. So if you'll see it properly here, okay, in this picture, so it is acting in the inner periphery and outer periphery. So we can write it is sigma into 2 pi. Okay, the periphery is given by 2 pi r, circumference is given by 2 pi r. So 2 pi ri, okay, 2 pi ri for the inner periphery plus 2 pi ro for the outer periphery. Okay, this is the surface tension force into cos theta, okay, will equal to weight is rho, weight is rho g v. Okay, so rho into v is given by mass into g, weight. So rho into v, so what will be v? V will be, here I want to again show you, so this area, okay, this area, so this area into height, okay, cross sectional area into height. So what will be the cross sectional area of the annulus? That will be pi by 4, sorry, pi capital sorry, outer radius, okay, ro square minus ri square. Okay, this is the um, cross sectional area of the annulus into the h, that is capillary rise. Okay, this is volume into rho, that is mass, into 9.81 or g, that is the, okay, formula for surface tension, capillary rise. Okay, now let's simplify it. So some terms will cancel out from each side, that is, okay, pi will go and nothing else. So now let's write them in a same fashion. So if you'll write them, okay, I'm taking out 2 common outside, okay, this pi also gone, 2 common outside. So I'm writing here 2 sigma cos theta, okay, into ri plus ro, this side will be equal to, okay, will be equal to rho into, okay, ro square minus ri square, the a square minus b square, it can be written a plus b into a minus b. So I am writing here ro plus ri into ro minus ri into h into g. Okay, uh, so ri plus ro gone. So from here we can write our formula. Let's write h in one side and other things in another side. So h will be, okay, from 2 sigma cos theta divided by rho g into ro minus ri. So this is our formula for the capillary rise in an annulus. Okay, h equal to 2 sigma cos theta rho g ro minus ri. So now let's use this formula in the current question to find out the h. Okay, so guys, this is our today's question. Okay, what will be the value of capillary rise when an annular tube of inner radius 5 mm? So we can write ri is given, that is 5 mm, we can write 0.005 meter, and outer radius ro is given 0.010 meter, that is 10 mm, and mass in liquid of density rho is given. So we can write 1000 kg per meter cube. Okay, and surface tension sigma is given, that is 0.020 Newton per meter. So in this formula that we have just derived, so sigma is given and theta is taken as 45 degree. Okay, theta is 45 degree. If not given in the question, take 0. So sigma is given, G we know, rho given, theta given, rho given, Ri given. So just by putting all the values, okay, we can get the capillary rise. So here I am writing H is equal to 2, sigma is 0.020, 0.020 cos 45, okay, cos 45, cos 45 divided by rho is 1000, G is 9.81 into, okay, Ro minus Ri, that is 0.005. So I am writing here 0.010 minus 0.005. So by calculating this, we will get our answer is 0.0057 meter. Okay, which can also be written as uh, 0.57 mm. So if you'll mark here, the capillary rise will always be very less. Okay, so this is all for today's, and hope you have enjoyed the video and learned the concept very well. So let's meet in the next video.